So thank you very much. Thanks for the invitation to come. Thanks to the organizers for putting all this on. This is a really nice way to get together, and I've never had such a well-prepared audience, I don't think, for this talk. So I love it. Thanks to everybody for coming to the summer school and putting in some work on the problems. It sounds like the problems were really good, the homework problems. Yeah. So I'm going to talk about Fubini-Bruhat orders. This is joint work with Stark Ryan. Stark actually is kind of local now. She moved to Chicago, and she happens to be on her way home from Australia, so she couldn't be here, but she's working at IMC Trading. Sounds like interesting work. And the outline of what I want to talk about is first let me introduce the Fubini words and some really interesting work by Brendan Pawlowski and Brendan Rhodes. Then their work naturally leads to some different kinds of posets, and one is contained in the next is contained in the next. So we've named them the decaf, the medium roast, and the espresso order. Seattle coffee is very big. And then with these posets, we have some new theorems that we're going to talk about. One is several of them sort of fill in with analogs of Ersman's criteria for Bruhat order. And the other direction that we've looked at is generalizing Fulton's essential set. So I'll tell you about those things and conclude with some open problems. Okay, so first of all, what's a Fubini word? On my way here, my sister was driving me, so she asked what I was doing. And when I told her I was going to give a talk on Fubini words, she said, well, will that help me with Wordle? Like, what's an example? And I was like, oh, no, an example is like, sort of 2, 1, 2, 3, 1. She didn't somehow think that was a word. But anyway, for you all, this probably is more natural. So a Fubini word is just any word in the alphabet 1 through K where you have to have every one of those numbers appear at least once in some fixed, you put them in an ordered list, but you can have multiple entries in this list. You can have the number 3 appear multiple times. And I tried to explain it to my sister as it's like you take all the cards in your house. You have some full decks of cards, but you put all the cards together, and now you shuffle them and put them in some order. That's a Fubini word. So 2, 1, 2, 3, 1, 2, 3, 1 has length 8. So we'll say this is an element in W83 because it fills out the numbers from 1 to 3 and length 8. Okay, so that's the notation that you have to write down. Make sure you remember what WNK is. It comes back many times. And of course, once you've listed out this word, a Fubini word, it always corresponds to a surjective map. Because you can take the numbers from 1 to n and just see where they go to in this word, right? And since you use the numbers from 1 to k, for sure, somewhere in there, this notation will give you a surjection. So think of those as exactly the same thing. Fubini word, surjective map. All right, so in many ways, the Fubini words generalize permutations, right? The permutations will be the surjective maps on 1 to n to itself, right? So that's easy enough. And then you can start asking, well, what other properties of permutations do Fubini words generalize? So you can talk about what's an inversion in a Fubini word, or what's a descent set, and what's a permutation matrix analog, right? So I don't need all of those, but the permutation matrix analog is most important for us. So let's make sure we define that. So this is very natural. So if you have your Fubini word W1 through Wn, make a k by n matrix. And in column J, put a 1 on the row corresponding to Wj. Right. So this is the transpose of the way Colleen was doing it yesterday when she said she was row-centric. I'm being column-centric. It's more natural in this context. So here's an example for 2, 1, 2, 3, 1, 2, 3, 1. The corresponding matrix is easy to fill out. All right, I'll call that M sub W. Okay, and so we have Fubini words now. They're kind of like generalizations of permutations. So you may ask, when you have Schubert calculus, the Schubert varieties are indexed by permutations. So could we generalize that concept? And what sort of Schubert theory should go with Fubini words, right? This is trying to motivate it as a question to you in light of the summer school, sort of to think about it. How would you do that? And one way that you might do this is start looking at k by n matrices, right? So let's take the k by n matrices over the complex numbers and think about the action of the lower triangular matrices that are invertible on the left of that. So B minus will be the k by k lower triangular matrices, invertible lower triangular matrices. And you could take the k by n matrices and mod out on the left by these lower triangulars and see what kind of cosets you get. Right? That's very natural. And that action corresponds to row reducing the matrix. So in each coset, there will be a unique element which is in row reduced form. So I look along row 1, and I find the first non-zero thing. If the matrices are full rank, this will definitely have something on the first row that's not 0. So wherever it is, rescale it to be 1, and then clear out the entries below that pivot 1. And then look on row 2 and find the first non-zero thing that's left, and rescale it to be 1, and so on. So you'll get a permutation matrix sitting inside of this, but you're going to have some columns that have not been, don't have a pivot 1, if k is less than n. And there's a way I can associate a type to this sort of family of matrices. In this case, the type will be the one that I was talking about, 2, 1, 2, 3, 1, 2, 3, 1. And I don't know if you can see off the bat how we associate the word to this, but what you're looking at is these pivot columns, and they determine the rest. So let me look at a bigger example to make this a little bit more precise. So here is the type of reduced row echelon form, row reduced form that goes with the Fubini word 4112513. All right, and how do you get this word? Well, you have to associate some extra data to the family here. So what we're going to pay attention to is where are those pivot 1s? What columns do they occur in? So in row 1, the pivot 1 occurs in position 2, and then where is the pivot 1 in row 2? It's in position 4, column 4, and so on. So for every one of the numbers from 1 to k, you see where the pivot 1 is, and write those down in order of where's the 1, where's the 2, where's the 3. So that'll be the vector alpha of w, corresponding to the word. These are called the initial columns. So 2, 4, 6, 1, 5 in this case. And associated to a Fubini word, there's also an initial permutation that we have to pay attention to, not just where are the initial ones, but sort of what order do they come in from left to right. So in this case, they come in the order 4, 1, 2, 5, 3. That is the underlying permutation matrix where the pivot 1s are. Easy enough to find. And okay, how do you fill out the rest of them? How do you get the other WJs corresponding to other columns? It's pretty natural that these go with, the first column should correspond to the label 4, and the second column should correspond to the label 1. But how do you get the columns which are, we call them redundant? They're columns that are in the spans of previous columns. And so WJ will equal the H element of pi if you have a non-zero thing in that position, and for all the pi i's that are greater than H, well, all the i's that are greater than H, pi ij is equal to 0. So we're paying attention to something like this word that Mark Schimmelzoner used yesterday. It's like a punch card. You've got these specified zeros, right, in some places. And you've got these 1s that have been determined by row reduction, and some other stars that are not determined at all. So those things determine the Fubini word, without being too technical about it. But this is how you do it. Okay, and one thing actually I wanted to say about these kind of matrices, it's not going to work quite right if I have an all-zero column, right? If I have an all-zero column, then what Fubini word, I shouldn't have zeros in there, right? So I don't have a good way to associate a Fubini word to the types of matrices that have all-zero columns. So let's just forget about those. Now, of course, you can generalize it. You could say a more general kind of Fubini word has all the numbers from 1 to k, and it has some zeros too, possibly, but they're not required to be there. But let's just forget about zeros for now, okay? And if you do that, this kind of Schubert theory that goes with these kind of matrices was given birth to by Brendan Rhodes and Brendan Pawlowski not that long ago, a couple years ago, and they defined the space of spanning line configurations. And that comes from the fact that each of these columns in these row-reduced forms, every one of those columns, if they're non-zero, does correspond to some line in complex k-dimensional space, right? And we have to have that, if you take all of those lines together, they form a spanning set because of the fact that we required that the Fubini word has the numbers from 1 to k, right? We said it was a full rank matrix. So the spanning line configurations are all these kinds of, I like to think of it as sort of pencils coming out of the origin. And they just happen to have a spanning line configuration sitting around my office, so I took a picture of it. This one is clearly spanning, right? This is sitting there in 3 dimensions, and any 3 color pieces of zone that you pick will be a spanning set. I wasn't sure if you know, it looks like I took the picture right head on. Those three are kind of in a line, but I think actually they're still spanning. They must not be quite lined up. Anyway, there's lots of spanning. And then there's other subsets in here which are clearly dependent too, right? Okay, so that's what we're paying attention to, these kind of dependencies. All right, now if I was gonna hand you a spanning line configuration, if it didn't come with a Zohm tool configuration, I would hand you a matrix, right? I'd hand you a K by N matrix where I wrote down some representative for each of the lines in the columns. So a typical example might look like this. And because I know that at least some non-zero thing occurs in every column, I may as well rescale at least one of the entries to be 1, right? That's so that I'm not telling you the same line in multiple ways, just to be somewhat canonical. And Rhodes and Pawlowski made a kind of clever choice in my mind, a very clever choice about which entry should I make into the 1. And it's going to be determined by which Fubini word corresponds to the cell that it sits in. So in this case, this one was an example of what we started with, because I just took the stars from back here, and I put in some zeros and some non-zero things. But I made sure to have a non-zero thing in all the key places so that it corresponds to the right word. Okay, so there's an example. Now, how does this, let's make this more concrete. So if you take the full rank non-zero matrices, full rank matrices, you can have some zeros, but no zero columns. Let's call that set of matrices FNK, all right? And then if you let Tn be the diagonal matrices, which are n by n, then we can multiply on the right by any diagonal matrix, and we would get another one of these matrices. So it's closed under that action. And so one of the lovely theorems that Pawlowski and Rhodes produced in their lovely paper is that this spanning line configurations is a smooth complex manifold. In fact, you can embed it into a product of projective spaces. And you do this by noting that there's a bijection from the spanning line configurations to these cosets, FNK mod the torus action Tn. And so then every one of those lines just corresponds to a point in projective space of k dimensions, and take the n tuple of those things. Okay, so that's very nice. A couple of easy examples. What happens when k is equal to 1? Well, since you have to have a non-zero thing in every column, and you can rescale that non-zero thing to be 1, this would just correspond to the 1-point configuration, right? And it's the all ones matrix. That's easy. What about when you have k is equal to n? That's the other obvious case to look at, right? Then you have the general linear group is what FNK turns out to be. So general linear group modded out by the torus on the right. It's a nice space. And it projects down to the flag variety G mod B by just quotienting out by some additional stuff. And it's really nice because it's homotopy equivalent to the spanning line configurations. So that means that the cohomology ring is the same. So it's clearly a nice way of thinking about the things that we already know and love in this new context, and more generally. So the original motivation by Pawlowski-Rhodes didn't come from this direction, motivating it from Schubert calculus and, hey, I want to have something that goes with Fubini words. I rewrote the history there a little bit. Actually, it comes from work that Hagelin, Rhodes, and Mark Shimizuno was doing on a really interesting ring that generalizes the cohomology ring of a Schubert of the flag manifold. They call this RNK. And it's very natural to take polynomials and n variables, and you mod out by all the kth powers of the variables and some of the elementary symmetric functions, the ones towards the end, higher degree ones. Okay, so that's some ring. It clearly generalizes the coinvariant algebra, which is just the case where you mod out by all the elementary symmetric functions. And it turns out that the nth powers will all be 0 anyway. So that ring has some nice properties in terms of the SN representation theory, and it connected in some ways to the McDonald theory. So that was looking really promising in the McDonald land. And Brendan Rhodes was saying, going around asking people, so what is the geometry that goes with this ring? That was really where the initial project came from. And this turned out to be a very good, really obviously the best choice, I think, that they could have found to find the spanning line configurations, because whenever you have a spanning line configuration of n lines, you obviously have an SN action on that. You can permute the lines, it's still spanning, right? And that SN action then induces an action on the cohomology ring, and this is exactly the same as the SN action on this ring, RNK. So everything is just fitting together beautifully. All right, so then they were digging in deeper. You know, how do we really understand these spanning line configurations? How do we see something like cells? How do we see something like varieties, just generalizing Schubert varieties? So this is already done by Pawlowski-Rhodes. And in order to get there, we have to define this thing called a pattern matrix. So if you have a Fubini word W, the pattern matrix P sub W is this row-reduced echelon sort of form matrix. Actually not, I shouldn't say echelon, because it's just the row-reduced matrix, right? You have these pivot ones, and in addition to that, in addition to your pivot ones, let's specify that there's a 1 in position Wj comma j for every j. But the other stars that are going to be in that row-reduced form, we leave them here. So this is not really, the pattern matrix is not sitting inside the k by n matrices with complex entries. It's sitting inside the k by n matrices with entries among just 0, 1, and star, okay, on that alphabet. But of course, in my mind, I conflate that with the set of all possible matrices that I could get by setting those stars equal to the complex number. So if you don't mind, I'm going to abuse notation and say this one that we already saw really sits inside this pattern matrix. Okay, easy enough. All right, and then, yeah, Mark? Yeah, right. You might as well think of those as entries in pk minus 1. Yeah, exactly. Okay, so, or I'm picking the A representative for every line in a canonical way. And I didn't pick this. Brendan Rhodes and Brendan Pawlowski picked it. Okay, so because we're modding out on the right by these diagonal matrices, and we can rescale, we don't really need to take the full lower triangular matrices, the B and K. We don't really need that because some of that diagonal stuff can just be eliminated by the right action by T. So it's actually more important to pay attention to the lower triangular matrices with 1s on the diagonal. This is the important group to pay attention to. So let's call that U sub K. U here for unitriangular, because the 1's on the diagonal. And what Pawlowski-Rhodes showed is that every single one of the spanning line configurations can be represented uniquely by a matrix in the product of these two sets, UK times the pattern matrix PW for some W, some Fubini word W, which has length n, and it's a Fubini word with k elements. Okay, so this is a unique representation. Every single one is complete parameterization of this space then, right? And so I like to think about what does this really mean in terms of orbits? This is saying that every matrix is in a unique orbit UK, not times PW, but times a specific entry in PW. Every single entry, if you fill in the stars, gives rise to a whole UK orbit that we have to think about. But you can also group them together and think about UK times PW. And since this matrix representation is unique, those sets will also be cells. What's the dimension of them? Well, it's going to be K choose 2 for the lower triangular part, and then plus how many stars there are in the pattern matrix. So let's call that number the dimension of W. The number of stars in the pattern matrix, that's the dimension of W. All right, so great. So they have some nice cells, very natural cells that live in this spanning line configuration space. All right, and then, so since they define these, we wanted to call them Pawlowski-Rhodes cells. It gets a little long to say Pawlowski-Rhodes all the time, so we started abbreviating them to just PR cells. And so CW will be equal to this unitriangular lower triangular matrices times PW. That's the PR cell. Okay, that's the central player. Any questions on that? Okay. So once you have these cells, then sitting inside the spanning line configurations, take its closure. You can do that in the Zariski topology because it all embeds nicely into the matrix space anyway. But it's not all of affine space, right? It's not sitting, it's sitting in some smaller space corresponding to these full rank matrices that have no zero columns. Okay, so the PR varieties are just the closure of the cells. And each cell, each C sub W is determined by certain spans and rank conditions, right? That's how we got there. So if you want to find equations, polynomial equations that vanish on these things, it suffices to look at determinantal equations that correspond to minors in the matrices, and whichever ones vanish on the whole UK PW. Those are the determinantal minors that define these varieties. Okay, I didn't want to write them down for you because there gets to be a lot of them pretty quickly. But we like this picture. Actually, this came up when Stark was preparing her slides as a template example in the background. And we like this because when you start thinking about how these PR cells and varieties sit together, they don't sit as nicely together as the Schubert varieties and Schubert cells do. They kind of feel more like boxes that were badly stacked up and might tip over. So this picture represents to us sort of some bad stacking of of these PR cells. Right, it's not a CW complex. They do have weird intersections. And so that's part of what makes it rich and interesting, I guess. So what is nice, though, something did work out that's nice, and that is that they don't have a CW complex, but what Pawlowski Road shows is there is a particular order you can put on the Fubini words that will make it into a paving by affines. So you can say this one is contained, this closure is contained in this closure, is contained in this closure, it's contained in this closure. And because you have a paving by affines, you get the nice fact that the cohomology ring is going to have a basis given by classes corresponding to these PR varieties. So they'll still represent a basis. And you can even write down these elements as elements in Rnk if you want to, so there'll be polynomials in that ring. And how do you get there? Well, you just take some Schubert polynomials that you've already heard a little bit about, and you specialize them and permute the variables in a particular way. So they explained all of that. It's kind of going in the wrong direction for the rest of my talk, so I'm not going to explain those details, but just know that they're out there. These are really playing nicely with cohomology. And in fact, the Poincare polynomial that goes with this cohomology ring is very closely related to a well-known Q analog of the Stirling numbers of the second kind. You do have to multiply by this Q analog of K factorial at front because of the UK action. But that all works very nicely. The actual Poincare polynomial, of course, we would plug in Q squared and we would reverse the order, but so it's close to this. It's the same, right. So everything is working out very nicely in this picture. And so this is why I was really impressed with all these results. There's a lot to be said for the direction that they've gone in. And it just felt very natural compared to what I know about Schubert varieties. So I wanted to dig into this. So what are some next steps in this theory? Well, one of the things that Pawlowski Road started but really haven't completed was studying the partial order on Fubini words that are determined by these PR cells and varieties. And okay, well, whatever that partial order is, it should be a natural generalization of Bruhat order. So we want to take everything we know about Bruhat order and see if it will generalize. And I also like this idea of what are the equations here? It wasn't really spelled out in the paper exactly how to do this. And I was struggling with finding the poset. So we really had to spell out the equations better. And then that naturally leads to, okay, well, if you have one set of equations, is that as efficient as possible? We know that determinants have lots of relations. So I like the work of Fulton on finding the essential set related to minimal sets of equations. And then more recently, I like this work of Gao and Young. In case you haven't seen it, a paper just recently, maybe a year or two ago, came out where they were finding the exact minimal set of equations, not just rank conditions. So this is a nice improvement. Okay, so all of these questions were in the back of my mind. And with Stark, too, we're interested in all of this. So let me explain how we're going to get there. So first of all, remember, just to remind you that Schubert varieties in the flag manifold are related to Bruhat order. It's a bit of a misnomer, the name Bruhat, because he didn't actually define this order. But let's stick with the name. And it's very easy to describe in terms of Schubert varieties. It's just that V will be less than or equal to W if their varieties are ordered by reverse containment. So XV contains XW. So they're ranked by codimension instead of dimension. That's natural. Okay, so that's one way to define Bruhat order, but then there's lots of other ways. Other people have identified simplifications. But one of the nicest ways, the way that Colleen described it yesterday, is also nice. And that's in terms of the covering relations. So we'll say that W is less than or equal to a transposition times W, if and only if the codimension goes up when you multiply by that transposition. And the covering relations are just to make sure this is minimal and you only step up by 1. This very well understood, this transposition rule, and then once you have the covering relations, you take the transitive closure of all those relations and you get the Bruhat order. And then another way of describing this reverse containment of Schubert varieties was the original one due to Ehresmann back in the 1930s, before Bruhat was involved. And that is a nice, efficient test, so that I think if you wanted to put it on a computer, this is a good way to do it. So if you have two permutations, V and W, you want to see if they're in Bruhat order or not. You take, for every partial reading, like for every prefix in the one-line notation for V and for W, you think of those numbers as sets. You write them in increasing order, and then as sets, in increasing order, you compare entry by entry. And if V sub 1 is less than or equal to whatever the smallest one in that collection is less than or equal to the smallest one for W, and so on, compare. So I'll use this triangle relation for this. We've started calling this the Gale partial order. Ardila, Rincon, Williams started calling it the Gale partial order. I wanted to call it the Ehresmann order for a while, but lots of different generalizations, and at least maybe we could converge on this name. It's helpful to have a name for it. Anyway, so the Ehresmann criteria is available and something we want to generalize. Did you guys talk about that last week, this criteria, or is that new? No? Okay, good. Well, I'm glad I mentioned it. Okay, and here, of course, is the picture that you know from S3. This is the Bruhat order, and we're thinking about the matrices being these pattern matrices that go with it. At the bottom, you see we have 3 stars in the one that corresponds to the identity because it's ranked by codimension. All right, and then how do you get the medium roast? The medium roast partial order, or medium roast Fubini-Bruhat order for its formal name, is just the exact analog of Bruhat order defined by V is less than or equal to W if and only if the Pawlowski-Rhodes variety corresponding to, oh no, I switched both. That should say that the one C sub V closure contains C sub W closure. I shouldn't have reversed both the inclusion. Yeah, sorry about that, I'll fix that. But, and so once you have this reverse inclusion, it completely clearly generalizes the Bruhat order. It respects codimension in the sense that if V is less than W, then the codimension of V is less than the codimension of W. That's in the right order. But it actually turns out that when you look at enough data, you start seeing that it's not a ranked poset under this. It's not a ranked poset at all for after a while. So for n equals 5, k equals 4, it's not a ranked poset. But the other thing that's weird, and this has to do with the weirdly way that the boxes are stacked, is it is possible for the Fubini variety, the PR variety C sub V intersected with C sub W to intersect non-trivially, but that C sub W is not contained in C sub V, or the closure. So this is what makes them weird and like poorly stacked boxes. All right, so then this means though that there's some other partial order that we could add to this. Let's say that V touches W. If when you take the closure of the PR cell for V, then it contains a point in CW. And we'll denote that by a little arrow. So V arrows W, it's actually a harpoon arrow. And we thought that looks like touching. All right, so then, okay, so from the touching relation certainly is implied. Whenever you have a reverse containment, you'll be touching, but there's more of them. And so this gives rise to this other partial order, which we'll call the espresso Fubini-Bruhat order. It's just the transitive closure of these touching relations. Pawlowski-Rhodes showed that directed graph is acyclic, so it does give rise to a poset. That was not obvious, at least to me, at all. So that's a nice piece of the puzzle that really does give rise to a poset. So here's a picture then. This is for Fubini words of length 4 with k equals to 3, and we tried to put all. Actually, we've tried to put all 3 orders. There's only, so far, I've only told you medium roast and espresso. But if you take all of the edges here, you get the espresso roast. If you throw away the blue ones, which are harpoons, you get the medium roast. If you throw away the red ones, we'll get the decaf order. Okay, so this is kind of like what they look like. And do you see anything interesting in this? So the colors are supposed to indicate something. There are 6 copies of the Bruhat order for S3 sitting there, right? So 36 elements, but because we're seeing lots of little S3s, you have to figure out, well, what is that coming from? Okay, so we we do understand this. It comes from the transposition rule plus one other rule that we know about. So the transposition rule on Fubini words is given by, we'll say, V. If V is equal to a transposition Tij times W, we like to multiply on the left because that transposition takes all the letters I and interchanges them with all the letters J. Okay? So if you have V is equal to the transposition times W and the corresponding initial permutation covers the initial of W covers the initial permutation of V in the original Bruhat order, then W will cover V in the espresso roast and the medium order and the decaf order, actually. And the dimension will be exactly one more. That, you have to prove that, but that works out nicely. It's easy. And then the other covering relation that comes out really easily is we call it the pushback rule. You can sort of take any one letter that is redundant, so it's not among those initial letters, and you can take it and you can sort of push it more in one direction or the other. So in this case, we're saying we'll push it back. If it was originally pi sub I, we can push it to pi sub I plus 1. You'll definitely change the dimension by 1, and you'll get a covering relation this way, too. So that's natural. So an example of the push back on the redundant 2 in the Fubini word 2, 1, 2, 3, if we push that second 2 to a 1, we get 2, 1, 1, 3. And you can sort of eyeball these and think about the closure relation on them. It's not so hard. Okay. Great. So if you just take the transposition rule then and the transposition rule and the pushback rule together, that's how you get the decaf order. Take the transitive closure of just those relations. And what's nice about the decaf order is then it is a ranked poset. And in fact, the rank function corresponds to this Q analog of the Stirling numbers of the second kind times the K factorial Qified. And I said you have to do this reversed. So when you do it reversed, you're really counting Fubini words by codimension. And when you do that, it works out to be exactly the Poincare polynomial for the cohomology ring. And this is all, this part connecting back to the Poincare polynomial, clearly using the work of Pawlowski-Rhodes. So here's the example for W43. Like I said, it has 36 elements, has a nice factored rank generating function. Okay, so that's some covering relations. And once we wanted to start studying these kinds of analogs of Bruhat order, we really had to get our hands on the equations that define these orders. And this is our philosophy, sort of when you want to study the orders, you have to study the equations. When you study equations, every time you find a new result about the equations, it implies something about the orders. Right? So to describe the equations in a better way, let me make some notation. So first of all, we're going to use the binomial coefficient square bracket n to mean square bracket n choose h to mean the subsets of size h among the numbers from 1 to n. And then we generalize that notation too. You can have square bracket n over square bracket k. That means take all the subsets from 1 to n that have sizes 1, 2, 3 up to k, any of those sizes. Okay, and then a minor on a matrix indexed by I and j will just be the determinant that you get by looking at rows from I, columns from j, that little minor. Right, that should be familiar notation. And then I don't know if you've heard this term before, flag minors. A flag minor is just where you take a subset of the columns, and whatever size that is, take the corresponding top rows of the same size, you get a minor. I like this terminology. It's been used by Bernstein, Fomin, Delavinsky in the 1990s. So let's use that. I would kind of like to call them northerly minors because they start at the top, but flag minors is definitely in the literature. So this is what I want to pay attention to, these flag minors. And why do we want to pay attention to flag minors? Well, it has to do with the construction that goes on with these cells. So we have our pattern matrices, right? And whenever you apply a UK, one of these lower triangular matrices with ones down the diagonal on the left, it'll change some of the minors in the matrix, but it won't change these flag minors because we're multiplying those flag minors by a little lower triangular with ones on the diagonal. So every matrix that's in the PR cell C sub W is going to have certain zero northerly, these flag minors, and certain ones will be non-zero, and that's what we want to pay attention to. So here, everybody comfortable with these minors, like the 2-2 minor of M in this case is -1, and the 3-3 flag minor, that one's a 0. But some other minors, like for example, the flag minor indexed by the columns 3 and 4, you can see from this pattern matrix, this could be anything actually. It doesn't have to be 0, it doesn't have to be 1, it could be anything. Okay, so let's then take the set of all subsets of the numbers from 1 to n of sizes 1 through k and partition them according to whether or not this PR cell either sometimes vanishes, always vanishes, which we'll call truly vanishing, so we have STU, and then unvanishing, means they could not possibly vanish on the spanning line configuration. So these are the important sets to pay attention to, S sub W, T sub W, U sub W. And so here, now I can write down all of these truly vanishing flag minors for a particular example for 3, 1, 1, 2, 3, because the list isn't so bad now. You know, some of them are size 1, some of them are size 2, some of them are size 3. But I found this very interesting when I first started studying this. So these flag minors give rise to an ideal, right? This ideal does not contain x21 as a variable, that degree 1 polynomial x21, which is the 2-1 entry. It will be 0 on this PR cell, and therefore on the variety. But this this degree 1 polynomial is not, it's not in the ideal generated by these flag minors, right? That's clear. Okay, so it's kind of surprising, and maybe to you, maybe it's not, that we can define the PR variety by just using these flag minors. This is enough. And it's only enough because we're sitting inside the spanning line configuration. It is not true that this ideal, which is a radical ideal, gives rise to the same variety as a different radical ideal if you're thinking about the affine space. It's just that on this subset corresponding to F and K, the full rank, no 0 column matrices, that this works. But this is, yeah, and because we know that there's something in every column, these kind of minors imply certain other relations that are not quite the usual determinantal relations. Yeah. So this was a nice improvement in terms of getting data. This really helped us to simplify the data that we were looking at, and we could study these various Fubini-Bruhat orders much better with this theorem. Yeah, so you can figure it out by looking at, you know, sometimes you just have a column and all the other subsets that contain it are in this flag minor ideal, and so in which case you'll know you have zeros. So there's a bunch of little lemmas. Say that again? Right. We're not doing that, but that might be a useful next step too. Right. And we know exactly what these unvanishing minors are. They're always going to be ±1. So it makes it easy to invert them. Okay, so we have a statement about equations defining these varieties. So we have a statement about the corresponding posets too. So the medium roast is then V is less than or equal to W if and only if the flag minors corresponding to V are indexed by sets that are contained in the flag minors indexed for W. Okay, that's the medium roast. And espresso roast, how do we do that? Well, this touching relation is just given by when do you have truly vanishing has to be inside sometimes vanishing and truly vanishing. That's natural too. And it turns out that this is if and only if the special matrix M sub W is contained, oh, that's a typo too. M sub W should be contained in C sub V. Closure. That one's definitely a little bit messy there. Sorry about that. All right, and we want to get something like the Ehresmann criteria. So what are we going to use for that? We're going to use this set alpha of W. Where was the first one? Where's the first two? Where's the first three? And so on. And we're going to use the Gale order, but we had to generalize it for multisets instead of sets. So let's say you have two multisets. Order the elements in increasing order, and we'll say that they're related in this Gale partial order if and only if the smallest is on the left is less than the smallest on the right. Second smallest is less than or equal to the second smallest on the right, and so on. And we can even extend it to multisets of different sizes. If we just think of every multiset as being padded with a whole bunch of infinities, and then you compare entry by entry again. So a shorter set will have more infinities, so it's more likely to be big. So 1, 3, 3, 5 is less than 1, 3, 4, 6, right? Because we compare entry by entry, but both of them are less than 1, 3 because of the infinities. Okay, and we have our alpha vector, alpha of W, so that has entries alpha 1 through alpha k. And we're going to use that to get an alpha vector for every subset J. So for every subset J sitting in the numbers from 1 to n, we'll let alpha sub J of W be the multiset. You have to count the multiplicities. The multiset of alphas corresponding to the WJs for J, everything in J. So for example, if we took alpha of 1, 2, 3, 8, that's a subset of the columns, I have to look at, okay, well, what is W of 1? It's 4. So let's include alpha 4. What is W of 2? It's 1. So let's include alpha 1. What is W of 3? Well, it's also 1. So we're going to include alpha 1 again, whatever it is. And finally, what is W sub 8? It's 3, so we'll include alpha 3 also. Right, so this multiset will end up being 1, 2, 2, 6 because you have to back-reference back up to what do these alphas mean. Okay, so easy enough to write down that construction for any J. So we have alpha J of W. And then these alpha J's completely determine the partition of all of these flag minors. So J is in the sometimes vanishing if and only if alpha 1 through alpha H for W is strictly less in Gale order than alpha J of W. It'll be truly vanishing if alpha sub J is not bigger than alpha 1 through alpha H, and it'll be unvanishing if these two sets are equal. So it completely determines it all. And in which case, then this says something about equations. What's the corresponding thing about the posets? So here for the medium rows, first of all, V is less than or equal to W in medium rows, Fubini-Bruhat order. If and only if, every time you have a subset J of some size between 1 and k, let's say its size is H, then you check, is alpha 1 of W through alpha H of W less than or equal to this alpha J of W in the Gale partial order as on multisets? If so, then we also have to have the corresponding thing happen for the V vector in order for everything to vanish quite right. Okay, and so in particular, we get something which is the complete analog of Ehresmann's criteria, that the subset alpha 1 of V through alpha H of V is less than in Gale order W, alpha 1 of W for alpha H. So nice generalization. Okay, and then what about for the espresso order? What we know best is these covering relations. So V touches W if and only if every time you have an equality of the alpha sets for W, then you also have to have a less than or equal to for V. So that's the way that works. And again, you get that this nice analog of the original Ehresmann criteria holds. Okay, so that describes the two orders that were remaining better, sort of the medium roast and the espresso order. The decaf order is pretty much completely understood. We don't have to talk about that again. And then any questions on those characterizations of the orders? Otherwise, I'll shift gears here for the last 5 minutes. Good. Okay, so since we found a better set of equations, a smaller set of equations to define these varieties, it's a reasonable question, did we get a small enough set? Could you do any better? And so we looked to Fulton's essential set as a way of trying to minimize these equations. So let me remind you of this nice theorem of Bill Fulton's from the 1990s, 93. So what is the essential set? First of all, you draw the diagram of a permutation. And it doesn't matter if you're row-centric or column-centric. Just, the diagram means you have these death rays. Everywhere you have a 1 in the permutation matrix, you shoot your death ray to the right and down. The points that are left are the diagram of W. Whether you call that, in this case, I guess I would be calling this 3, 5, 4, 2, 1, but you can call it whatever you want. Anyway, you get this diagram, and then how do you get the essential set? You highlight the southeastern corners of the connected components. So those are in squares. Okay, easy enough. Once you have the diagram in front of you, it's very easy to find the essential set. And the really nice theorem is that a matrix is, an n by n matrix in this case, is in the Schubert variety XW if and only if the northwest rank, so if you look at the IJ component and look at the rank of the matrix in that northwest of there, that little submatrix, if that rank is less than or equal to the corresponding rank in the permutation matrix, then this matrix M will be in the Schubert variety. And this carries over to the matrix Schubert varieties in the affine sense too. And you only have to do, so that's the original definition of Schubert varieties, but what Fulton said is you only have to check these rank conditions on coordinates I and J, which are in the essential set. So it reduced the number of checks. And he proved that this is actually a minimal number of equations, minimal number of rank conditions on these varieties. You can't get by with fewer than these elements in the essential set and still define the same variety. This doesn't mean that you have a minimal number of equations because of the fact that determinants have relations among them, and that's what Gao and Young were improving on. Okay, so what's the analog of that for the Pawlowski-Rhodes varieties? So we had to do something like the essential set. We knew that. You can write down something like a diagram of a permutation as well. It didn't work quite right off the bat because of the fact that you have multiple letters and they can be interspersed however you want. But if you take a corresponding word, so here I have a long word, I guess, 4, 4, 2, 5, 3, 1, 3, 6, 5, 4, 1. Take all the 4s and shove them to the left because 4 is the first letter that you see. And then the next letter that you ever see reading from left to right is a 2, so take all the 2s and shove them left. And then take all the 5s and shove them left. And by doing this, you'll get what Pawlowski-Rhodes call a convex word. Now all the i's are right adjacent to each other for every value I. If you do that, then you could extend that word to a permutation by just taking all of the redundant columns and thinking of them as indexing an increasing sequence that's down below the row K section. And you would get the diagram of a real permutation this way. It would be exactly the same diagram, but that diagram has no bubbles below row K because everything is increasing. So we'll just pay attention to the top K rows. So this will say is the diagram for every word that convexifies to the same thing. And then what is the analog of the essential set? We'll just take the southeast corners here. So you might have extra stuff along row K. That's okay, but you have these southeast corners. And for us, it's really important that you also, in your essential set, you do have to pay attention to what is the rank. So we'll make this into a triple instead of pairs. But you'll have triples H, beta I of W, and R will be in the ranked essential set if, oh, I have to tell you what a couple things are. So first of all, H, comma, whatever the size of this beta I set is a southeast corner in the diagram. The beta I's are very natural things to pay attention to. This is just going to be the columns that are indexed by the letters which are in the initial part of the permutation, pi 1, pi 2, up to pi I. That's what beta I is, all the columns that have one of those letters in them. So this will be a growing set of sets. And then the rank conditions come from what is over the whole PR cell C sub W, what's the highest possible rank among the columns in the beta I positions. So if you have this data sitting there in front of you, then we claim that you can check if a matrix is in a particular Pawlowski-Rhodes variety if and only if it satisfies the rank conditions for the essential set, this ranked essential set. And that's easy enough to test as well. And so just to write out the philosophy again, so every theorem about equations, there should be a natural analog for the partial orders. So what is it going to be in this case? Have you thought about that before, actually, what the essential set says in terms of Bruhat order? I hadn't thought about that connection before. Before the philosophy was already in our mind. So the analog of this is, suppose V and W are Fubini words, then V is less than or equal to W in the medium roast order, if and only if every time you have a constraint in the essential set, there's a corresponding constraint for V. There's a corresponding constraint in the essential set for W. And what is that constraint? Well, we can write it out in terms of the size of these beta I versus beta J sets. And so there is an analog of that for permutations too. And so this means that we can reduce the number of checks for Bruhat order down to the size of the essential set. Okay, so one thing I didn't mention, but there's an improvement of the Ehresmann-Tableau criteria that Bjorner and Brenty did. I don't know if you've seen that, it's in their book. They say you don't actually have to check every single row of the Ehresmann table, just the places corresponding to descents. And because of this theorem on essential sets, we get something like that for the Fubini orders too, the Fubini-Bruhat orders. So something of a little bit of an improvement. Okay, so let me conclude then, I'm a little over time. This project is not done, it's work in progress. Hopefully the paper will come out soon, by the end of the summer, I'm hoping. But one of the things I think we're gonna have to leave open is how do you describe all of the covering relations for this medium roast order? We don't have anything quite as nice as the transposition rule. So this is getting complicated. At least this gives us a way to find more data, but we're finding more rules and more rules and more rules. We haven't got it nailed yet. And this was the original question that Pawlowski and Rhodes were asking. And wide open out there is what other properties of Bruhat order are shared with these Fubini-Bruhat orders? That's natural to ask. And what's the smallest possible ideal that even does carve out this C sub W set inside the spanning line configuration? And then, of course, what is a minimal set of equations? That would be nice, too. And then as I was listening to the talks yesterday, they were all so good. You know, I started thinking about everybody's philosophy and how does this relate to Fubini-Bruhat orders. So Mark says we should always double. So yeah, let's double these kinds of Schubert polynomials. And Liz said that orbits are alcove walks. Now, I don't know how that applies here, but I hope Liz will figure this out. And shellable, right? Aram said something. There are a lot of open problems about post sets, and are they shellable or not? I really haven't tried yet. So that's wide open. Okay, thanks for listening. This is my collaborator, Stark Ryan.